In this video, I'm going to help you understand what the rate law is for a chemical reaction. I'm going to show you how we can write an expression for the rate law and how we can determine the orders of reaction with respect to individual reactants. But most importantly, I'm going to help you understand what all this actually means. In order for there to be a chemical reaction between any two reactants, in my example here, I'm starting with hydroxide ions and bromomethane, we require there to be a collision between the two reactant molecules. And these collisions have to have enough energy to overcome the activation enthalpy. And often our collisions have to have the correct orientation in order for them to be successful. This is a good example. My hydroxide ions need to approach the carbon atom from the opposite side of the leaving group. The leaving group in this case is the bromine. If my hydroxide ions collide with any other orientation, the collision is not going to be successful. The reaction is not going to proceed. But generally speaking, we can say that for any chemical reaction, the rate of the collisions is going to be proportional to the concentration of our reactants, in this case hydroxide ions and the bromomethane. And square brackets, as always, denotes concentration. We can express this as a rate law. And the rate law would look like such. Rate equals K OH minus in square brackets bromomethane in square brackets. So that is our rate law, sometimes called a rate expression. K is our rate constant, and it's specific to this particular reaction. It has to be found experimentally because its value depends on the size of the molecules, their speed, and the fraction of collisions which have the correct orientation and sufficient energy to overcome activation enthalpy. We can determine the rate of this reaction by measuring how the concentration of either the reactants or products changes over time. Let's start by looking at the concentration of the hydroxide ions. Well, as the reaction proceeds, the concentration of hydroxide ions is going to decrease because the reactants are being used up. Let's say I would like to know the rate of the reaction at this particular time here. So I would draw a tangent to the curve at that particular time. And then if I figure out or calculate the gradient or the slope of that line, that will give me the rate of the reaction. So the gradient of this line is going to equal the change in the y-axis. So that's that difference there. So change in the y-axis divided by the change in the x-axis. So if I mark that, it would be that value there. So essentially what we're saying, it is the change in the concentration of the hydroxide ions over a specific time interval. The units would be, well, concentration is in moles per decimeter cubed. In this particular example, it looks like time is in seconds. So whatever the gradient is, the rate would be, I don't know, let's go with 1.3 mole per decimeter cubed per second. Now, although the rate is just the rate, in this case we went with 1.3 mole per decimeter cubed per second, the gradient is negative because the concentration of the hydroxide ions is falling. So technically it would be minus dy, minus the change in the concentration of hydroxide ions divided by the change in time. But the rate is expressed just simply as a positive number. We can also measure the rate of reaction by measuring how quickly one of the products appears over time, in this case bromide ions, and the graph would look like so. The concentration of bromide ions is increasing with time because it's the product. Now, if we take the time at which t equals 0 and we were to, again, draw a tangent, figure out the slope or the gradient of that line, that would give us, so gradient, in this case it's a positive, so it's simply dy over dx, in this case change in the bromide ion concentration over the change in time. This would give us the initial rate of reaction, the rate of reaction at t equals 0, which is always going to be the fastest rate of reaction because it's when the concentration of the reactants is greatest. We can write a rate equation on the rate law for any chemical reaction once we have found out experimentally how the rate depends on the concentration of the reactants. This is really important. You cannot predict the rate law just by looking at the balanced or stoichiometric equation. We need to do the experiments to find out how changing the concentration of each of the reactants affects the rate of the reaction. Now, for this particular reaction between hydroxide ions and bromomethane, the rate law is found to be as such: rate equals K CH3Br square brackets to denote concentration raised to the power of 1, hydroxide ions raised to the power of 1. The reaction is said to be first order with respect to bromomethane and first order with respect to hydroxide ions. I know this because the concentration of each of these reactants has been raised to the power of 1. And the reaction is said to be second order overall. So although each concentration is raised to the power of the order of that reactant in the rate equation, if it's a 1, we don't usually bother putting it in. Hence, we would see the rate equation look more like rate equals K CH3Br square brackets OH minus square brackets. But what does that even mean, that a reaction is first order with respect to bromomethane? Well, what it means is that if we double the concentration of the bromomethane, we double the initial rate of reaction. And if we plot a graph of initial rate of reaction against the concentration, we get a nice straight line that passes through 0. It's going to pass through the origin because there's not going to be any rate of reaction if I have no concentration of reactants. Moving on to the reaction between bromate ions, bromide ions, and hydrogen ions. Well, experiments show that the rate equation for this particular reaction is rate equals K BrO3 minus, that's our bromate 5 ion, bromide and hydrogen ions raised to the power of 2. So the reaction is first order with respect to the bromate 5 ions. It is first order with respect to the bromide ions, but it is second order with respect to the hydrogen ions. And 1 plus 1 plus 2 makes 4. It's fourth order overall. So what does this actually mean? Well, what it means is that if I double the concentration of either the bromate ions or the bromide ions, the rate of the reaction will double. But if I double the concentration of the hydrogen ions, the rate of the reaction will quadruple because it is second order with respect to hydrogen ions. Let's look at this on a graph of initial rate of reaction against concentration. Well, As we've just said, it is second order with respect to hydrogen ions, which means that every time this experiment was done and the hydrogen ion concentration was doubled, the initial rate of reaction quadrupled. And when you plot concentration of hydrogen ions against initial rate of reaction, we get this curve. Alternatively, if we plot initial rate of reaction against the hydrogen ion concentration squared, then we get a straight line that passes through the origin. And finally, let's look at a dehydration reaction, dehydration of bromomethane to form ethene. When we do the experiments, we find that the rate equation looks like so. Rate equals K CH3 CH2 Br. And that is it. This reaction is first order with respect to the bromomethane. It is zero order, so zero order, with respect to the hydroxide ions. So what that means is that if I double or triple or quadruple or halve or change the concentration of hydroxide ions in any way, it has absolutely no effect on the initial rate of reaction. The hydroxide ions are clearly a reactant, but they don't take part in the key rate determining step. This is a reaction that takes place over many steps, and the key step does not involve the hydroxide ions. So just to recap, if we take any reaction and we do a series of experiments to find how the concentration of each of the reactants affects the rate of reaction, we're then able to write a rate equation or the rate law for that particular reaction. So let's say rate equals K a to the power of 2 B. What this rate law or rate equation is telling me is that if I double the concentration of reactant A, then the rate will quadruple. And if I double the concentration of reactant B, the rate even would double. If changing the concentration of one of these reactants had no effect on the rate of reaction, it would said to be zero order with respect to that reactant, and it wouldn't appear in the rate equation. And K is our rate constant. Now, as always, if you hit the link in the blurb below, it will take you to the Crunch Chemistry website where you can find the notes for this video as well as some practice questions. And if this has been useful, then please hit the like button and subscribe. It makes a huge difference to a small channel like us. I look forward to seeing you next time.